Hi everyone, my name is Leon Starr, and I am the technical lead of Toyota Research Institute's Woven Planets model-based systems engineering team focused on building platform-independent models of the real-world driving environment. My team still works for Toyota, but we've recently transitioned from an environment that is research-oriented to one focused on production. And we think this is a good thing since now we are even more focused on safety. The open source project I announced last year, as well as our MBSE team, is intact and we are continuing our work. Toward the end of the presentation, I will give a status update on our project. But the focus of today's talk is on the motivation behind our work, with special emphasis on its relevance to requirements and validation. First, a quick word about our new home, Woven Planet. I dug through our warm, fuzzy corporate slides and landed on this one. As engineers, we feel compelled to deliver as many intelligent features piled on top of one another as quickly as possible. But that is not our goal here at Toyota. Feature deployment only matters if we can maintain trust and ensure safety, not just for the passengers of our vehicle, but for those of us walking, bicycling, driving in the surrounding environment, and not just for early adopters, but for our parents and grandparents. I drive a Camry, and I can tell you that it has prevented me from smacking the wall in my garage and backing into pedestrians and cross traffic more times than I would like to admit. Not all advanced driving features are necessarily that reliable and easy to control, but they really should be. And ensuring that advanced, ultra-intelligent driving features have these qualities is what motivates us to model the real-world driving environment. In case you haven't seen my video presentation from last year, here's a quick recap. Last year I presented an example of an unprotected inside turn intersection traversal. In the USA, an inside turn is to the left, so an unprotected left. Our work is platform independent since the models apply regardless of driving platform, and in fact they would work just as well observing a human driver. As far as the models are concerned, you either execute the maneuver correctly or you don't. So our models function kind of like an automated driving instructor. Early this year, I published a Medium article describing our work and announcing our open source GitHub site. Feel free to go there and browse our wiki where you will find our models, documentation, and links to more videos and resources. There's also a discussion group where you can ask questions and leave comments. Today I'm going to focus less on the models themselves and more on our motivation, anticipated uses, and, in general, why we think this work is essential to getting safe, reliable, automated driving on all public roads. And a big part of that has to do with requirements and validation. I'm sometimes asked if modeling fits into the big V of the ISO 26262 standard, or if I think the V is even relevant to model-based engineering. And my answer is directed at the horizontal arrow where you validate against your safety requirements. If your requirements are incomplete, ambiguous, or otherwise inadequate, so will be the validation. In other words, validation is only as good as the requirements. And this brings us to the real question. How good are your requirements? I've been in the business of modeling system specifications for a few decades now. Yeah, I really don't like saying the D word, but here I am. I've seen many methodologies and attitudes toward requirements definitions come and go and evolve. There's always another new book or consulting company to tell you how to write good requirements. And of course, there are a variety of useful techniques to learn. There are quite a few I like to teach. But there is one limiting factor that you just can't escape. You can fight against it with all the techniques you have, but at some point you soon get diminishing returns and just end up wasting a lot of effort. This is one of the reasons that Agile became so popular, with many developers thinking we don't need requirements at all. That critical impediment is, ready for it, English. Or any other native language. I mean, if you think about it, human language was never designed for writing requirements for large complex systems. Now, I don't think I'm saying anything controversial here. I suspect that you're all familiar with language's failings when it comes to requirement specification. In my experience, I've worked with requirements for medical systems that have to go through FDA approval and a wide range of other safety and mission-critical systems. You can spend a short afternoon scanning through any requirements database of any large project, and I'm sure you'll spot the following. The same word used to mean many things. Different words used to mean the same thing. One requirement that contradicts or conflicts with another. One requirement described in painstaking detail, while another similar requirement inexplicably glossed over. Something missing. Or not. What could it be? Staring into the dark abyss of a doors database, how can you tell? And because requirements are written by humans, you begin to notice personal differences in writing style. Sometimes you can even tell who wrote what just by the choice of words. That in and of itself tells you that the process is more art than science. The larger and more complex the system, the more people involved, the more these deficiencies multiply. What's happening is basically 1, we're only human, and 2, we're using a language evolved to converse efficiently in a social context where the listener fills in the gaps with their own context, assumptions, and bias. Natural language is great for storytelling, but not so much for systematic safety coverage. It's actually even worse than that. In his book Logic and Databases, C.J. Date references a dialogue where a committee attempts to write a single rule requiring dogs in a park to be on a leash. They manage to boil it down to a requirement after a few attempts, but the end result is still ambiguous. I've included it here for your entertainment in the unlikely event that you decide to rewatch this video. Date uses this example to demonstrate the value of predicate logic. The problem, though, is that reams of predicate logic is not the easiest thing for most subject matter experts to digest. And that brings us to MBSE, Model-Based Systems Engineering. Models give us a way to capture our requirements with logic and bring it to life through simulation in a way that mere humans can interpret, and we can use our models to reinforce our otherwise sloppy language. Our models deliver a variety of benefits that reinforce written requirements. I'll go into these in some detail in the next few slides, so I won't read them all off here. But basically we use semantic models to define a precise and logically consistent vocabulary. The modeling language represents an application of predicate logic that we can instantiate with driving environment data. But unlike raw logic expressions, the models are a lot easier to read. So you get the benefit of unambiguous logic without all of the upside-down A's and such. We build state models on top of our semantic models. These models formalize the continuously changing relationships between the ego vehicle and various modeled elements of its local environment. Taken together, our models provide an executable specification of how a system should behave. Now, written requirements are still valuable. For example, natural language can be easier to understand, provides a narrative context, and is helpful when it comes to categorizing functional features for easy reference. But by letting the models do the heavy lifting when it comes to logical consistency and completeness and keeping our terms straight, we don't need to spend near as much time banging ourselves on the head trying to achieve literary perfection. It just boils down to choosing the right tool for the job. Now let's dig a bit more into some of these features at the base of the pyramid. One of our first modeling steps is to define a precise and unambiguous vocabulary. And when I'm trying to sound smart, I use the word semantics instead. Why is it so important to have a precise vocabulary? The quick answer is that you can't solve any complex problem without one. Consider the problem of working out the area and eccentricity of an ellipse without a vocabulary. If the only terms you have are, say, center and squashiness or flatness of the shape, you're not going to get very far. But once you are armed with an adequate vocabulary, semantics, the problem practically solves itself. This isn't just true of ellipses. I observe this principle all the time in solving driving problems. I don't know about you, but I've been in more than a few meetings where experts attempt to describe an intersection or other driving environment with widely varied and inconsistent and slippery definitions. Of course, everything magically gets sorted out in the code, right? In fact, it often gets sorted multiple times, in multiple places, in multiple ways. And that is just one reason why we need a common set of rules and definitions outside of our code. Here is a quick animation showing how some of the modeled subsystems on our open GitHub site establish a vocabulary for angular intersections. I'm just going to fly through them here. Feel free to browse the wiki on our GitHub site and leave any comments in our discussion group. I'll give an overview of each of these subsystems towards the end of my talk. I do want to point out that the process of defining these vocabularies alone has led us to discover numerous edge cases, even without building a single dynamic model. This comes as no surprise since I have gotten this result in a wide variety of applications before I arrived in the automotive space. For some reason, the edge cases jump up and down and wave hello as part of the semantic modeling process. When you know that your model must execute correctly, it compels you to take every little component of that model seriously, just as you would with code. In our case, it forces us to think deeply about the problem in ways that filling out a JAMA or DOORS database just won't. In the example here, execution of our lane change state table reveals a lot of unexpected states in transition associated with the various ways that a simple lane change can fail. In my experience, models that you cannot execute are rarely of much value. Without execution, disagreements descend into rabid philosophical and opinionated arguments. Now, at this point, you could argue that execution is achieved by code. So, why not just write code? Well, code is a platform-specific implementation. By necessity, it must incorporate tons of intricate implementation details that are not required or desirable in a system specification. And then there's a whole issue of transparency. Let's spend a minute on that. Transparency is all about having models that can be easily read, questioned, argued, and verified against subject matter expertise. We're so used to this idea that the only folks who think deeply about how a system works are the developers, since they're the only ones with that executable focus that I just talked about. That's no longer true if we are building platform-independent executable models. Machine learning experts and C++ programmers are not necessarily experts in safe and legal driving, transportation systems, and road structures. In this slide, I have two subject matter experts discussing a safe and legal process for negotiating an unprotected left turn. Note that they aren't relying on any implementation or platform-specific terminology, and we formalize this expertise in our turn movement models. And having done that, the reasoning behind the logic is directly visible in our models and model documentation. By the way, we don't just draw diagrams. Each model element, every attribute, class, relationship, state, and so forth is documented and justified with real-world examples. So if you doubt that a modeled concept is valid, you can examine the backing examples and edge cases and explanations to determine whether you're right or wrong. In many cases, you may be right. The models are often wrong. In practice, it is not that difficult to guide a non-modeler subject matter expert through any given model and elicit lots of useful commentary and insight. So my point here is that models like those we are building formalize and make driving safety rules visible to non-developers. And it is this transparency that forces us to see our mistakes quickly and resolve them. There are a lot of problems to model in the ADAS space. Why focus on the driving environment instead of vehicle sensing, control, and planning? To answer that question, let me walk through a few observations that led me down this path. First, we can observe that the driving environment is relatively stable. The structures we drive along, roads, lanes, driveways, crosswalks, and so forth, are pretty much the same as they were decades ago. Also, the rules of the road haven't changed much either. They vary from region to region, but the way you proceed across a train track or a crosswalk or how you make a lane change has pretty much remained the same. There are some changes, of course. Scooters in traffic, for example, and the greatly increased presence of shared and dedicated bike lanes in the US. But these are geologic time frame changes compared to the pace with which our driving platform technology is continually advancing. Now, if we consider all the capabilities of an AV and think about all the possible situations it can find itself in, driving is really complex. But if we consider the local driving environment at any given time, it's not so bad. At any given point in time, the environment offers few safe and legal maneuvering choices. I took a few snapshots from my dash cam to demonstrate. In this first shot, all I can do is stay where I am, creep forward a bit, or maybe change into the lane on the right. In fact, I can't even do that since there is someone speeding down the lane just behind me. In this next one, I'm committed to rolling through the intersection and maybe slowing to park on the right or continue forward. I should not be initiating a lane change in the middle of the intersection. In this next one, I have a few more options. From a macro behavior level, it is almost as if the environment is dictating your options and guiding you along. By focusing on the local environment, we narrow the problem space. Therefore, it suggests that it is often the case that our focus from a safety perspective should be on modeling the environment rather than the AV itself. I would go a step further and ask, if you don't have a precise definition of the environment and fundamental driving behaviors supported by that environment, how can you possibly validate behavior with any degree of certainty and completeness? So rather than inventing validation scenarios one by one ad hoc, we leverage our modeled environment to generate a complete set of scenarios systematically. I want to take you on a tour of the models we now have available on our public GitHub site. They are all still in the early stages with much more work to be done, so we make no claims that they are complete. In fact, in the process of putting these slides together, I found a number of items I will be scrambling to fix in the coming days. But I think we're at a good starting point, and we do have plans to expand our efforts. So think of these as stakes in the ground rather than comprehensive models at this point. The driving environment models are part of a single subject matter we call the vehicle guidance domain. This is in the sense that local restrictions of the driving environment is fundamentally what guides the vehicle's available movement choices. This domain is defined by a single large semantic model of the entire driving environment. But for management purposes, we organize closely related semantics into their own subsystems. At present, this consists of the road, intersection, crosswalk, lane, reconfiguration, and ego subsystems. Clearly, there are at least several more we need to add. For example, we haven't incorporated freeway on-ramps just yet. Here's a brief overview of each of these subsystems. We began development with the road subsystem. As such, we have a bit more documentation available there. In fact, you'll find 6 explanatory YouTube videos linked on the wiki site for that section. Our focus here is on lane divisions, various types and usages of lanes, flow of traffic, and partitioning of traffic flows, as well as the continuity of roads through regions. It is in this subsystem that we know whether we are in a region where traffic drives on the right or left sides of the road. We also deal with the orientation of left and right from the perspective of the ego vehicle. As the name implies, here we are interested in the structure of intersections. We haven't added our roundabout models yet, but those have been sketched out and will be incorporated soon. The focus at this point has been angular, signalized intersections. In a future presentation, we will be demonstrating how we've modeled all possible movements through such an intersection. We're also interested in the various yield requirements on unprotected turns and such. The lane reconfiguration subsystem answers the question, what are all possible ways a lane can originate and terminate? This leads us to consider not only merging and diverging lanes, but also lanes flowing into and out of intersections, mid-road turns, cul-de-sacs, and dead ends. The current concept is to model all these features as variations of longitudinal, lateral, and internal lane reconfiguration. Behavior-wise, this is relevant when analyzing multi-lane change scenarios where the lanes could be reconfigured in various ways mid-maneuver. A systematic characterization of lane arrangements puts us in the position of generating a comprehensive set of lane change scenarios. The crosswalk subsystem represents an analysis of a wide variety of crosswalk structures. The trick here was to determine the fundamental principles behind crosswalk construction so that we could explain intersection crosswalks that hop across multiple islands using the same or different walk signal spans. As I described in my video last year, we seek out the fundamental building blocks for defining crosswalks and then look at all the possible combinations to anticipate unusual crosswalk configurations. All of the other subsystems describe relatively static environmental structures. In the ego subsystem, however, we consider how the ego vehicle interacts with elements of the other subsystems. Consequently, this is where most of the state models live. For a lane change maneuver, for example, we model the relationship between the ego vehicle and its target lane during a lane change. For an intersection traversal, we model the changing relationships between the ego vehicle and various components of the intersection. This is primarily the entrance lane and entrance crosswalk, the selected movement and selected lane-to-lane connector, as well as the exit crosswalk. Note, by the way, that we use the term ego vehicle and not autonomous vehicle. Our models don't care what level of automation is available. They are only concerned about the resultant behavior, not the mechanism by which it is affected. All right, so I've got a 3-part summary. First of all, requirements validation and MBSE. The quality of validation can only be as good as the quality of the safety requirements. Natural language is seriously limited when it comes to requirement specification for large, complex, safety-critical systems. If you don't let MBSE do the heavy lifting for you, you're either going to spend way too much time and effort on written requirements that in the end will have limited value, or just give up and let the developers figure it out on their own. Safety requires that we have a coherent and complete model of the real-world driving environment, because that's what constrains our safe and legal driving choices. And finally, all of our open source models, as well as links to our talks, articles, and videos can be found here. Feel free to browse our models and wiki, leave comments or questions in the discussion group, or just say hi. And feel free to reach out to me directly via email or LinkedIn.